Hello and welcome to this episode of the Adventures of OS. What we're going to cover today is Chapter 2. And in Chapter 2, we're going to communicate with our operating system. In order to do that, we're going to program something called the UART, the Universal Asynchronous Receiver Transmitter. In order to do that, we're going to have to program it in Rust, as we do everything else here. And so the first thing I'm going to do, as you can see on your screen, or if you're just listening with the audio, first thing we're going to do is create a new Rust module called UART. And so how Rust makes its modules is it's sort of like a new C++ file or something like that, and we automatically include that through our lib.rs. So essentially all I'm going to do is create uart.rs, that's our Rust source file, and then later we'll link it into our lib.rs so that we can actually access those UART functions. So the very next thing we're going to do is go into our new generated uart.rs. If we look at this, it's empty. There's nothing in there, but that's exactly what we want. So the very first thing we're going to do inside of uart.rs is create what is known as a structure. Inside of Rust, we can have structures. Inside of C++, we have classes and structures, which essentially mean the same thing. Inside of Rust, a structure just occupies memory space, and then on top of that, we can actually implement member functions like we can in C++. So the very first thing we're going to do is, inside of the Rust modules, pub sets the visibility. By default, everything in Rust is very closed. For example, if I do let without the mute, it creates an immutable variable. And if I don't do pub, and I just create a structure called UART or something like that, what's going to happen is it won't be visible outside of this module. And so we want UART to be visible so that we can use it. We want to be able to use it somewhere else, and inside of everywhere we need to call print line. And so this is the very first thing we've done, pub struct UART. Essentially, we can actually leave it like this. We're allowed to have zero-sized structures just like UART, and then we can implement functions just on top of that. However, I'm going to store one additional thing, which is the base address. So in the system that we're programming for here, the base address is 0x1000,000. So I've written it on the screen there. And that's essentially just a memory address they chose. They're like, oh, we're going to pick this memory address. That's going to be where the UART goes. So let's go ahead and put our base address in here just in case it changes. So this will give us a little bit of flexibility when we start writing our operating system for different systems. So for now, the system, if we just want to put 1,000,000 in there, that's fine. But just to see how structures work inside of Rust, let's go ahead and put the base address. So what I'm going to do is pub struct UART, and then we open brace, close brace, and inside of there, unlike C++ or something like that, we specify the name first, followed by a colon, and then what is known as the constraint. The constraint here is essentially the type. So in this case, I say usize. Usize stands for unsigned. Size is a type that contains a different size depending on what architecture it is. Everything else in Rust, where you have U32, U64, that tells you exactly how many bits that's going to take. However, usize on a 32-bit system takes 32 bits. However, on a 64-bit system, like the one we have here, usize will take 64 bits. Now, the reason I'm using usize here is because whenever we start using raw pointers in Rust, it likes a usize because it knows that the pointer size of that underlying architecture is going to be the exact same size. So if we don't use usize here, we have a lot more conversion to do there. So there we go. So we've written our structure. That's essentially all we need for now. Now, to get this structure to actually do something, remember, the thing we're trying to do is communicate. And communication is read and write. Or in Rust, we use the print line macro, something that looks like that, or just the print macro. And we're going to use macros in Rust. We're actually going to write a few macros in Rust and see how the meta programming actually works inside of Rust. But one thing we want to start doing is essentially there are three operations we need to perform for the UART. Number one, initialization. Get everything ready to go, everything good. And then step two, read. Step three, write. So we're going to call read get because we get a single character every single time we read from the UART, and the write we're going to call put, because every time we write to UART, we write one character at a time. And so put and get sort of let you know that, hey, we're not writing the entire thing all at once, we're just writing it byte by byte. And so to actually start implementing member functions of a structure, we use IMPL. IMPL, obviously that's your implementation, and then the keyword IMPL is followed by the structure's name. So it looks something like I have on the screen. Impl, we'll just call it that. Impl UART, open brace, close brace. And now inside of here, we can actually define the member functions that we want. So the first one I want is I want to actually wrap the structure. So the structure, all the structure is it gives me access to member functions that know about the base address. So in here, these member functions are going to be esoteric to this UART device. That way there I can initialize, I can get, and I know as long as I have the proper base address inside that base address structure, we know we're going to either write or read from the correct place. So first things first, let's create our wrapper. Typically in Rust, we use the new, which is just a function that returns the structure. Now you can see capital self actually refers to the structure. I could actually put capital UART in there if I wanted to, but Rust actually provides a convenience wrapper here called self. And self refers to the structure itself. And so in this, all we're going to do is wrap a new UART structure. So this is how you create a structure in Rust. You just mention it by name, open brace, close brace, and then inside of there, you initialize what you need. So in this case, I'm just going to initialize base address. Rust has this unique feature in which, notice that base address here matches the exact same base address that I'm passing inside the function. So the structure has base underscore address, whereas new also has base underscore address. And so I don't have to specify, I can just put base underscore address, and Rust is smart enough to match base address from the function, the parameter to the function, to base address the member inside the structure. And so what this does is, now that I'm not adding a semicolon, which you can see on the blog, this is actually going to return in the entire structure. So it moves it. Remember, Rust is strange in this, and it's not like C++. C++ always wants to copy things out. However, inside of Rust, we're going to move UART out of here. So it's essentially a temporary that we just created in line 9 through 10. It's just UART open brace base address close brace. And what Rust is going to do is move this new structure that we just created out and then return it as the return value out of new. So there we go. So new is what is called a static member. That means I can call new without an instance of a UART. I'm going to differentiate that with this next function, which is going to be our initialization function. So once again, we want to make it public so that we can access it. And fn, obviously that's your function. And then I'm going to add this mute self. Notice in this case, self is lowercase. So unlike this, which is in C++, it's more the Python style where self refers to the memory address where this UART structure is located. And so I'm not going to return anything because I just want it to initialize and be done from there. So now I have access to the base address member because this is not a static function. Hopefully you can see the difference between new, which does not have a self parameter, and init, which does have a mutable self. That means with the mutable, I can actually change the actual structure itself. But I'm doing this because we're actually going to set a raw pointer to the base address and start getting everything going. So first things first, raw pointers in Rust. We do let pointer equals the self. So this is how I refer to the structure itself. And remember, we have the base underscore address, okay? Now this is of type usize. And remember I was telling you, usize conveniently wraps to a pointer. And so I'm going to use the as keyword, which is how we typecast inside of Rust, and convert it to a mutable U8 pointer. So U8 stands for unsigned 8-bit. And essentially that's going to be our character. So we're just going to grab 8 bits at a time, 1 byte at a time from this UART driver, and that's what we're going to do. So in here, this is our base address. We don't really care what the base address is while we're writing this. We just have to know the certain offsets from there. And so inside the document that I've shown on the blog, we can see that offsets 0, 1, 2, 3, 4, and 5 are essentially the ones we're going to use. So first things first, if you remember back to the blog, the very first thing we want to do to our UART is set the word length. The word length by default is 5 bits. And we want to set the word length to 8 bits. That way there we can utilize the entire transmission and receive registers. So in Rust, we're going to use the raw pointer by doing pointer.add. Now add allows me to add just like pointer arithmetic inside of C++. So we don't do pointer plus, the plus operator is not overloaded here. So we do pointer.add. And inside the parentheses inside of add, that is where we're going to specify what register we want. And so if we look back at the technical reference document of the UART, we can see that base plus 3 is what's called the line control register, or LCR. So I'm going to put a 3 in here. And what that's going to do is essentially add 3 to the base address. Because this is a U8 pointer, the size of one add, it's going to be 3 times 1. So essentially this is adding exactly 3 to the pointer itself. So that moves us to the line control register so we can start executing instructions. So the next thing we need to do is set the word length. Bits 0 and 1 need to be 1 for us to have an 8-bit word length. So what I'm going to do is use write volatile, or volatile, however you want to pronounce it. So in this case, if you remember back to C++, we actually have a volatile keyword, and that allows it so that we can tell the compiler, hey, don't optimize this out, because behind the scenes, whatever we're writing to can actually change behind the scenes. And it just helps us with the compiler so it doesn't optimize out what we're trying to actually do. Now, the 2 bits that we want to set, once again, are 0B stands for binary, so I'm binary 1, 1. And that's going to be bit 0 and bit 1. So right now, with this one line right here, we just set the word length to 8 bits. Now what we need to do is set the FIFO. FIFO stands for first in, first out, and essentially it's a little piece of memory for our transmit and receive registers. So I can just stuff the FIFO. I can just stuff 8 bits at a time in there, and it's just going to push them out as fast as it possibly can. And so to enable that, we have to go to the FCR register, which is base address plus 2. FCR stands for FIFO control register, so if I do pointer.add, we do another write volatile, and it's bit index 0. So all I have to do is write a 1 into there, and we've just enabled the FIFOs. Next, we want to enable the receiver buffer interrupts, which is called the IER register, which is at offset 1. The IER register is the interrupt enable register, and what we're going to do here is add 1 to the base address and enable it by running a 1 into there. So most of these are actually sitting at bit index 0. That's why we're writing 1s in there. And so it makes it fairly simple, fairly straightforward to do that. Now, one thing I do show in the blog is the divisor. I'm not going to do it here because it actually doesn't make any difference for this emulated version. And so the last thing that we need to do here is, one thing you'll know about Rust is whenever we use raw pointers, it is deemed unsafe because we're allowed to just set a pointer to whatever memory address we want. And what we're doing on line 15, where we say pointer equals self.base address as star mute U8, we're saying, hey, Rust, I want you to take this base address and make it a pointer. I know what I'm doing. I'm going to look at that memory address, and I'm going to use it as I see fit. And so now what we want to do is, if we add the keyword unsafe, we're allowed to execute unsafe Rust, like adding to pointers, writing to pointers, reading from pointers, things like that. But we're guaranteeing to Rust that if you want to operate properly, that we know what we're doing. Well, since we know the base address, we're not error checking the base address, but we're just going to go with it and say, okay, we know what we're doing. So we're going to put unsafe, and everything that is unsafe will go under that block. So just like so, notice that we have an unsafe open brace, close brace, and everything in there, we're telling Rust that, yes, we're now going to guarantee the safety of these. Essentially what we have here is 3 different writes to a pointer. So there we go. That is how we're going to write in it. Now, before we go any farther, let's go ahead and take a look at lib.rs, because in lib.rs, this is actually where we want to write all the utilities to connect to our UART driver. So if you remember back to chapter 1, we had a Rust modules section down here. Now, we didn't have any modules back then, but now we do. We have the UART module. So what we're going to do is we're going to import a module by saying mod UART. Now, once again, Rust will make that module private by default. So I put pub mod UART. And what that's going to do is it's going to look for either a folder called UART or a Rust file, .rs file called UART. And we'll import it into our system. So let's take a look at what we've got so far. Now, lots of this I've already written from the actual blog post itself, but in this case, print is what we're going to write. So in Rust, we actually have a write macro. So in write macro, it essentially takes 2 parameters or multiple parameters. The first parameter is going to be, what do you want to write to? So in Rust, we have what are known as traits. Inside of a trait, it's essentially an interface if you know Java, or it's an abstract class if you know C++. So these traits, there's one trait in particular that we're going to use for this write macro. I'm going to delete it because Rust doesn't know it's there. Inside of here, we're going to implement the trait. So implementing the UART, like we did on line 7 here with impl UART, is how we actually can add members into the UART driver itself. To actually add the trait, what we're going to do is we're going to import the trait into our Rust file here. And to do that, we say use. So just like using and stuff like that inside of C++, we just say use. And then the core library is build, almost to the brim. It's supposed to be a smaller, pared down standard library, except this is platform independent. So we can actually just move the core to wherever we want. And so in here, we're going to do format, error, and write. So trait write is the one we're actually looking at. Error, you'll see why we need to import that as well. But right now, write is the trait that we're going to import. So what we're going to do to actually implement this interface known as traits inside of Rust is we're going to say implement write for UART. So this is kind of a weird syntax, but we say impl write, so the trait comes next, and then actually the keyword for, F-O-R, like a for loop. And then the class that I want, or the structure in this case, that I want to implement. Now the reason it's now giving me a red line under there is because just like an interface in Java or an abstract class in C++, we have to implement everything that's inside of there. So in order to actually implement the write trait, there is what is called a write_str function. So I'm just going to write it out here. You can actually look at the documentation and follow along to see what this is. So the first parameter for write_str is the class itself, mutable. So a reference to the mutable class, or a mutable reference to the class. And then the string that we want to output. So in Rust, we have what are called string slices. And in this case, we actually have a string reference that we've got here. And that function is going to return what is called a result. Results automatically imported into Rust. And a result could either be okay, or it could be an error. And so that's why we actually imported the error, because the first half of result inside this template is the okay. If it's okay, what to return? And we're essentially returning what's known as the unit type. We don't really care that what the data is that we return. Essentially, we're just giving the information that yes, is succeeded, or no, this caused an error. So let's take a look at how we're going to write this code. Inside of here, str has a couple of helpers that we could use. One of the useful ones is to get an iterator for all the U8, which is actually kind of nice because that's what we're dealing with inside of our driver here. And so what I'm going to do is use a for loop. So inside a for loop, I'm going to say for a certain character inside, and I called my string out, O-U-T. So I'm going to do OUT.bytes. And what that does is .bytes will give me an iterator of all the U8. So essentially just byte by byte of the string out. And so what I'm going to do is I'm just, remember what we said the UART does. We put one single byte at a time. And in this case, I'm actually going to grab from the string one byte at a time. And so in this, I'm just going to say self.put. Remember, we're going to write a function called put, and its job is to write to the UART transmitter. And what we want to write is C. Now, when we're done with that, remember, the write_str is expecting a result. It's either okay or it's an error. In this case, it's always going to succeed. We didn't error check anything, so it's always going to succeed. Okay, so notice we do have put. It doesn't know what that is because we haven't written it yet. But okay, we have to return the unit type. That's why there's double parentheses here. Because if you look at result, it's expecting a unit type. All right, so now that we've got that written, now we can actually link that into our print line using the write macro. And we'll do that a little bit later. But right now, let's go ahead and write the functionality for put and get. And so these are fairly straightforward functions because inside the NS16550A, say that 10 times fast, we actually have a transmit and receive register hooked to the exact same place, and it's hooked to the base address. So let's go ahead and write put. So I'm going to do pub fn put, take a mutable reference to self, and then a single character U8. So once again, what we have to do for all of these is we have to create a pointer. So technically, I guess I could use the structure itself to store the pointer, but in this case, I'm storing the base address. It doesn't really matter how you choose to do that. If you store the base address as a U size instead of a pointer, we have to create a pointer every single time we want to do something. However, that might be a better way to do it because we know this is going to be an unsafe operation. So every time we create the pointer, we know we need an unsafe block here. And all we're going to do is write. So we're just going to say pointer.add 0. So I technically don't need the add 0. I can just say write_volatile. However, the reason I'm doing this is for clarity that yes, we are going to the register 0. And if we write to register 0, that is our transmit register. and I'm just going to write C directly to it. So let's talk about get. Now put, essentially what we're going to do is we're just going to write to it. Because we're using a FIFO, what this is going to do is it's going to push it into that FIFO. And whenever the UART gets a chance, it's going to output that. For get, it's the other way around. Now it has the exact same base address, but when I read from the receiver, I'm going to get a character. However, what if the receiver is empty? Well, luckily for us at the line status register, which is base address plus 5, we actually have a DR bit, the data ready bit. And if that bit's a 1, that tells us, hey, there's data ready for you to actually extract here, and then I could return something. Otherwise, there's not. And so that tells us something about the return that we need for get. Get needs to be either returning the value that we were able to get from the receiver, or we have to flag that we weren't able to get anything. And luckily, Rust provides us a convenience wrapper for that called option. So let's go ahead and write get. So it's going to be a public function as well. And it's just going to take a mutable reference to self, and it's going to return what is called an option. Now, option is nice because it has two options with option. Either sum, which means it succeeded. In that case, we actually give it, and notice I put U8 inside the angled brackets here. We're going to return a U8 within sum. Otherwise, if we were unable to get something from get, or something was not in the receiver, then we're going to turn what's called none, N-O-N-E. And when we do that, we could actually check that value to make sure we actually get something, or if we got nothing. And so let's take a look at what we're going to do. Once again, set our pointer. And then unsafe block. Now what we have to do is check the line status register. Base address plus 5. So let's do an if statement. We'll do pointer.add5. Remember, this is how we get to the line status register, and we're going to read it. And remember, this is a U8 pointer, so this reads all 8 bits. And what we're interested in is bit index 0. It's the very first bit, so we're going to mask it with 1. So we end it with 1, and we're saying, okay, if that's equal to 0, what that tells us is that bit, that DR bit, is the value 0, so there's no data waiting for us. And so we're just going to return none. Otherwise, we'll use an else statement here. We're going to return something. And inside of something, we put whatever we want to return inside the parentheses. Well, if you think back to it, the receiver is at base address 0. And if I receive, or if I read straight from the receiver, we're going to get an 8-bit value, which is the character that I want to return. So I'm going to do pointer add 0.read_vault. There we go. And so now we have put written, get written, and so now we can continue with what we've got. So notice now impl write for UART, that's the trait write, is all happy. So let's take a look at back to lib, which is the master file here. And so whenever we look back at lib, what we're going to do is we're actually going to populate print here. So notice print line is already done because print line just calls print and adds, it concatenates the \r\n, the new line characters for that, or carriage return new line. So what we're going to do is for all traits, we have to import them into here every single time. Now, the reason I have these little braces here is because I want to create a new scope. The reason is because this is meta programming. It's just like a macro programming inside of C++. What Rust is going to do is whenever I call print or print line, it's going to take out print line with the exclamation point and substitute whatever code I write here. And so we have to be very careful not to intrude on the scope that's already there. And so we create our own scope so that we are sort of self-contained inside of here. Now, Rust requires that all traits be imported when we're going to use them. And so once again, we have to import the write trait. There we go. And then what we're going to do is use write. So the very first thing that Rust expects for here is the actual driver that implements the structure that implements trait. Now what I'm going to do here is type in crate, and I'll show you why. We can actually type UART if we're in the lib, but we have to type crate. So what we're doing here is walking a path all the way to this UART driver. So let me double check on UART.rs. Notice we have the UART right here, okay? And what we're doing is we're walking our way to this path. So we're walking Rust all the way to find our UART structure right here. And so inside of there, what we're going to do is create new. Now, if you look at new, it's static. That's why we use the double colons there, called the scope resolution operator. And what we're doing is we're calling this function. So this function takes a base address, and it's going to give us back a UART structure. And so the base address that I want to give it, I'm just going to hard code this in here right now, which is 1,000,000. So remember, in this architecture system that we have so far, 1,000,000 is where my UART memory is located. And then finally, what I'm going to do is I'm going to pass it the rest of the arguments. So if you notice on line 13 here, we have $args:_TT and then a plus. That plus tells us, or tells Rust, that we have to provide one or more arguments. It's just like a regular expression in that case. And what that argument could be is anything that is what's called a token tree. And that gets down to the language itself. So it has to be some sort of language token to be considered viable for this macro. And so to actually just write those, whatever the user gave us, or whatever the programmer, us in this case, gave print, we're just going to do the exact same thing. So $args with the plus, what that's going to do is it's just going to put all the rest of the args after the write. And so what this does is write, because we've implemented the trait, whenever we want to write, it's going to pass the string into our write_str. Well, our write_str is going to convert that into bytes and use self.put to put each one of those out into the FIFO, the first in, first out, the transmission or the transmitter. So now that we've written that, let's go down to the very bottom, double check that we have written pubmod UART. That's actually how we import it. And now let's take a look at compiling. So barring any typos or mistakes that we made, let's go ahead and type make, see what happens, okay? So we've done a few things, and we're now starting to get these warnings, and it says, okay, what is going on here? And it's telling us warn unused must use on by default. Okay, so what this is telling us is that write is going to return us what is called a result. So core result, it's essentially going to say, here, did it either succeed or did it fail? Just like the result that we returned whenever we did get, or I'm sorry, not get, but write_str. Let's go back to it real quick. So if we go to write_str, you can see we returned a result. Well, Rust, because we're returning a result, expects you to check that to make sure that it's not an error. Well, for this, we really don't care, because if it's an error, well, nothing's going to be printed to the screen. So there's nothing we can do anyway. And so with Rust, we're just going to say let underscore equals. And what that's going to do is the underscore is not a real variable. It's just saying, okay, we're acknowledging that you're returning a result, but we don't care. We're just going to ignore it for now. Okay? So now let's go back and let's try to recompile. So these were all warnings, so it actually did compile, but now we got rid of the warnings. So now let's take a look at what I've already written inside of main. Inside of main, what I've done is I've initialized the UART. So once again, notice I create a new UART driver for every invocation of print line. Well, in this case, for every invocation of write. Now that's fine, because all the structure's job is to hold that base address that I give it. And the whole reason we're using the structure is so that we have access to that put, the get, and the init, those member functions that belong there. And so line 84, which is my_UART.init, what that's going to do is take the structure and call the init member function from there. And there we go. So we initialize it. What that's going to do is set the FIFO register. It's going to set the word length, and it's going to enable interrupts. Now, we're not going to listen to interrupts yet. We're not quite there yet. But now what's going to happen is whenever we call print line right here, this is a macro, and we specify a single format operation, it's going to call this second arm right here. So the first arm right here is if we call print line without anything inside the parentheses. If we only put one thing inside the parentheses, we're going to get the second arm. If we put one thing in the parentheses, which is the format string followed by the data I want to put inside there, we get this third arm. And so essentially what we've done is that print line is now going to concatenate \r\n and call print. So now we move up to here where our print was, and what's going to happen is we let Rust know we're going to use that trait that we've implemented, and we're going to call write on that string that we just got. And so remember, once again, the string write_str essentially converts it into bytes, and we put out each single byte. So let's take a look at what happens when we run this. Okay, so we get, this is my operating system, I'm so awesome. If you start typing something, I'll show you what you type. Now, I've already written this before the video even started, but let's go see what happens. So down here, this is where this is my operating system comes from. If you start written Rust in like native x86 64 or something like that, that's how you're going to write to standard output. EPRINTLINE would print to the error, standard error. And so this is where that language is coming from. So THIS space is my operating system is printing to the screen. So remember, what happened behind the scenes is we converted this entire string into just a list of bytes. So T gets printed, H gets printed, I, S, space, I, S, and so on and so forth, gets pushed to that transmitter, and the UART transmits it over here. Now that's what we're doing here, and let me just highlight it. This switch for QEMU is dash serial mon : stdio. And what that says is connect the UART to standard input and output. The mon stands for monitor. And essentially what we're going to do is we're hooking our standard in and standard out to the serial driver of this quick emulator. And that allows us to use the UART to read and write to our system. So let's take a look at reading. So that is how we actually can put characters. Now, I've already written this, but essentially all this, the rest of this main does is loop. So this is an unconditional loop, and this is going to loop over and over and over and over again. Now, if you remember, get returns an option. So it either returns none or returns some. And so this is sort of a new primitive, a new if statement that I've never seen before until I started Rust. It's called the if let. And what that's going to do is it's going to say, okay, let sum and in parentheses C equal my underscore UART.get. If you remember, .get returns an option, and an option can either have some or none. So in this case, what we're asking for is we're saying, okay, call .get, and Rust is either going to return a sum or none. In this case, because it's inside the if statement, we're saying, Rust, only let us enter this block if you give us something. And what we're going to do is Rust will put that something in whatever we put in the parentheses. In this case, we put the lowercase c. So it's a variable called C that will get whatever we put inside the sum. Now, if you remember, what we put inside the sum was read underscore volatile of the receiver. And in there, we get a U8, 8 bits. And so inside of there, we have essentially a character. Now, character in Rust is a little bit different than a character in C++. All I'm going to do is refer to a character as an 8-bit value. And so a match is almost like a switch statement inside of C++. And so what we're going to do is we're going to say match C. And inside of there, we specify each case that it can match. Now, unlike a C++ switch statement, we have to provide all possibilities. Now, luckily, we don't have to specify all 256 possibilities. Instead, we can put this underscore with an arm, and that's just a fat arrow. It's equals greater than sign. And what that's going to do is that's the catch-all. So if none of the above match, we come here, and essentially we just print out the C as a character. This is how I can type, and whatever I type prints to the screen. So if I don't type what's called 8, what is the number 8? 8 is a backspace. So anytime I type the backspace key, what we're actually going to do is we're going to backspace, which all that means is move the cursor left by one place. Then we write a space and move it back. Otherwise, if we didn't do that, it wouldn't actually erase the character there. It would just move the cursor back one. Okay, so let's test that and see if that works. So I'm going to type something, hello, and then I'm going to hit backspace. We hit backspace. What that essentially did is moves the cursor back one, erases by putting a space in there instead of the O, and then moves the cursor back. So now we have hell. Funny how that works. So then let's take a look at the next arm where we have 10, and then this, the pipe, is OR. So we're saying if it's 10 or it's 13. If you know anything about that, 10 is the new line character and 13 is the carriage return, which is \R. And essentially what we're going to do is we're just going to print out the first arm of print line, which is a new line character. So if I press enter here, we're going to get a \R, and that moves us to the next line. Then we have V's, 0x1b. So maybe some of you are familiar with these. These are ANSI escape sequences. And this is how we can handle errors. This is how we can handle colors. A lot of terminal operations start with 0x1b. Now the thing about this, remember, get and put use 1 byte at a time. The 1b is an escape sequence that says, hey, listen, there's about to be more bytes. And so what we do is we actually use the same idiom, if let, and we grab those additional bytes. And that allows us to actually handle the arrow keys. Otherwise, you're not going to see them. So if I press up, we get that's the up arrow. If I press down, that's the down, left, right, and so on and so forth. And to quit the emulator, we press Control-A and hit X. And so you can see how this code is matching what we have on the output. Okay, so now that we've done that, make sure you have macro_export. If you don't have that, unfortunately, the rest of the modules that you write aren't going to see that. However, as we are now, because we've hard-coded 0x1000, we've initialized it, feel free, go crazy. Now that you can communicate with your operating system, start seeing if you could write just a rudiment shell. I mean, we got sort of one here. Just a rudiment shell here at the end of k-main and see what you can do from there. And we'll get to it in a later discussion. That's all I have for now. Thanks for sticking with me, and welcome to Chapter 2. Hope you had fun. I'll see you next time.